Okay, so I guess just let me walk through how we did it, then I'll put the values in. So we're taking, again, this is one step of the mechanism where we're taking methane and we're halogenating it. So we're doing a CH substitution. So in this, this reactant side of this step, we are cleaving the methane CH bond. So from our table 6.1, we recall that had plus 435 kilojoules per mole. And so then we're taking that value and we're adding the enthalpy for breaking the HX bond, where X is the halogen, and these are just from the table as well. So if we take 435, subtract 569, we get 134. So to plug in the remaining values, we get plus 4, plus 67, and plus 138. So again, think about what this is telling you. As this step of the entire mechanism proceeds, with fluorine, it's exothermic. It's generating a lot of heat. Chlorine is barely endothermic, and then we're increasing the endothermicity, meaning that for this reaction to proceed with these halogens, you have to supply heat. So what step 3 is telling us is that this is a chain reaction in which the X, the halogen radical, propagates back to the second. So this heat that is required here for chlorine, bromine, and iodine, the heat needs to be generated from step 3 so that when this radical goes back in, it doesn't die and it can propagate this cycle. So on this step, the X2 values we did up here. So that's what we use here for each one. And then fluorine, chlorine, bromine, and iodine for methyl X. Again, these are all evolving because they're on the product side, so we use the negative sign. So our values here, we have negative 297, then negative 108, then negative 100, and negative 83. So before we move on to the next question, where we're actually going to look at what these numbers mean, let me just again explain this process of what's happening. We're taking methane, and then we are comparing all the halogens, so that's why I'm writing X2. Then we are making the different halomethanes plus the HX. So this substitution of H for X, this is a radical halogenation. So the mechanism proceeds through this methyl radical, and the overall process, even though we're showing this one arrow here, this overall one arrow really consists of 3 distinct steps. So we have initiation, which is cleavage of the halogen to the halogen radical, propagation. The halogen radical abstracts the hydrogen from methane. We generate the methyl radical plus our HX. The methyl radical then reacts with a second equivalent of the molecular halogen to generate our product, the halomethane. And then this is the propagating radical. So in the chain reaction from 2 to 3, X goes back in. So the heat produced in this second propagation step here must be greater than what is required for the first propagation step to occur. Does everyone follow that?
I have a question. I can tell where you got the math for number 3 on fluorine, but I am not really understanding the rest of them, like where the numbers are coming from. Because the negative 297, the positive 159 from the X2, and then the negative 456 from the CH3F. But if you do the same pattern for the Cl and CH3, it doesn't follow, or Br.
What specifically did I miscalculate?
Well, for chlorine, CH3 and chlorine, I got negative 351 for that value. So negative 351 and 159.
So let's run through this here real quick. So X2 for chlorine. So chlorine, we're using this X2 here. Cl, that's our plus 243, right?
I didn't do it that way. I thought that the X2 would be plus 159. Because that's what it was for fluorine.
Yeah, that's fluorine specific value.
Yeah.
So
Yeah.
if you go from this table, I can't see what's on my camera because it's like not showing up, so I don't know if you'll see this. But we're looking at the XX bonds. So
yeah.
for fluorine we use the 159 and then minus 456 to get 297. For chlorine now.
Okay, I understand now. You're going to use a 243.
Yeah,
all
we're
right.
243 and 351. So what do these numbers mean? And again, we'll put them in sort of a different format on the next thing, but just let me explain it now. So for this step 2 to proceed with fluorine, you need this much heat. So you don't really need heat because it's evolving heat. This is also evolving heat. So what this tells you is that fluorine, when you use it in this process, fluorine is crazy promiscuous. There's so much heat generated, it does not care what type of hydrogen CH bond you have. It's going to substitute pretty much everywhere. Now look at the difference here. The sign flips from chlorine or fluorine to chlorine. Step 2 now requires 4 kilojoules per mole of energy, but step 3 is giving off negative 108 kilojoules. Because this is exothermic, it is sufficient to keep step 2 going. And the same for bromine. But notice that bromine requires a lot more, right? You're going from 4 to 67. So this is evolving negative 100. Now, iodine is the one that flips. Step 2 requires the most for iodine. See this number? How it does not match that number? Step 3, which is the second propagation step, is not evolving enough heat for this radical to go back into this step and carry the chain forward. So really what we're only considering for chapter 10, practically speaking, is chlorine and bromine. We say that chlorine is very reactive and bromine is selective. And so in the latter part of this worksheet, we'll understand what that means. But let's go to this, where I'm just really rewriting these values and summarizing what I just said. So when I say step 2 divided by step 3, all I'm doing is taking that number 297 divided by 134. That gets you 2.2. So for fluorine, both steps are negative. So we say fluorine is too promiscuous. That means, again, when you look at a molecule and you classify the types of CH bonds present, fluorine really does not care in terms of tertiary, secondary, primary, because there's so much heat generated, it can satisfy the abstraction value for pretty much any of them. So for chlorine, we take 108 divided by 4, that gets us 27. So we say chlorine is reactive, but not selective. And again, the practical meaning of that, when you're given a molecule and you classify, okay, I have methyls, I have primary, secondary, tertiary hydrogens. Chlorine is able to provide enough energy that it can pretty much go after all of them. Now compare that to bromine, where the ratio of 100 divided by 67 is 1.5. So we say bromine is more selective. So we can say, to put it in Instagram terms, bromine is posh. It really wants to go after a select type of carbon-hydrogen bond to abstract. It's very picky because there's only so much heat produced in that propagation step that it wants to go for the hydrogen that it can abstract. It doesn't have enough energy to abstract the stronger CH bonds. Then 83 divided by 138 for iodine is 0.6. And we say this is not not reactive at all. So it does not have enough energy to abstract the hydrogen atom and propagate the chain. Is everyone clear on conceptually where we're going with that? And again, I can't see you, so you can be making faces or flipping me off. It's the wonders of Zoom here. I don't know why it operates different each time, but it does. So let me go to part 7 now. And so part 7 is where we really put all this together. So in part 6, we examine the trend of halogenation in general for methane. So we're only dealing with methane there. Now what we're going to consider is the relative reactivity data for chlorination versus bromination. So again, we're leaving out fluorine, we're leaving out iodine because fluorine's way too reactive. Iodine's not reactive enough. So we're really considering on these two sides. The left side is chlorination, the right side is bromination. Now this is general for any structure you're given. So what do we mean here? CH. So for a primary versus secondary versus tertiary. So this is the type of hydrogen. HCl is that product that's consistent for chlorination. And we add those values. We do the same thing, but for HBr here. Then we're going to compare these numbers to these numbers, and we're going to plot them on a reactivity coordinate diagram. So again, for our first column here, we want to look at our table. We look at the table, we find, okay, what is the value for a standard primary hydrogen? So we're going to use plus 410. And so that's consistent amongst the chlorination and bromination. So just so I know you all understand what I'm asking, what value should I write for the secondary CH abstraction or homolytic bond cleavage? The secondary CH. So what value should I put here and there? So Aiden says plus 397, that's correct. And then for the tertiary, what value should we use? Plus 381, says Cole and Mac. Then we saw from the prior page, the value you were using for the HCl cleavage is negative 431. So all we're doing now is we're just adding these together to get this column here. So for the primary, we have negative 21, and again, these are all kilojoules per mole, negative 34, and negative 50. So for HBr, we're using negative 368. So that term is common amongst all primary, secondary, and tertiary. We then sum them. Now maybe if we have a brave soul out in the audience today, can anyone in a sentence or two in the chat explain the difference in these values? Again, the constant amongst chlorination and bromination is this column here. We're looking at a primary hydrogen versus secondary versus tertiary. So for a primary hydrogen, when you use chlorine, this step evolves negative 21 kilojoules per mole. For bromine, it requires plus 42. So conceptually, what does that mean? So yeah, in the process, as Hannah and Mac allude to, chlorination is much easier amongst these types because you're always evolving heat no matter what. And again, we say that chlorine is not selective because all of these values are negative. So when you look at bromination, we say this is selective because there's only so much heat that is produced in the bromination reaction. So in bromination, which type of hydrogen is most easily abstracted? So your choices are primary, secondary, and tertiary. So the answer is tertiary. And again, probably a way, and I'll show this on the next slide, but a way you want to conceptually think about this is, again, everything's sort of relative. We don't really know the absolute energies. So this is all relative. So say we're here, and this is sort of our 0 point for energy. So there you have no kilojoules per mole into the system either way. For bromine, so we'll say plus is bromine, and by plus I mean we're going up. For chlorine, it's negative, we're going down. So here we have, this is sort of our energy, and this is just a way to conceptualize this. If you're putting energy into the system for the bromine case, the number that you hit first is 13, right? If you're going up, you hit this first. Then you hit 29, then you hit 42. So if the bromine radical is looking for a hydrogen to abstract, it's going to abstract the first thing it sees, and that's going to be that value of 13. So, you know, in a sense, the chlorine is opposite because there's so much energy produced when you're going the other way to negative. Even though you hit negative 21 first, remember that the chlorination reaction produces so much energy, it's really not selective in following, say, like a linear scale. And again, that's due to the excess of energy that is produced because it's exothermic. So questions on this concept of comparing chlorine versus bromine with the different types of hydrogen. So again, I can't see your video, so you'll either have to unmute or write something in chat. So the next thing says plot the delta H for each versus time for the substrate indicated. Let me draw that substrate again so it's more on the screen and we can see it. So there's 2-methylbutane. So I just wrote a column there, primary, secondary, tertiary. How many primary hydrogens are in 2-methylbutane? Primary. So Ian says 3, 6, 9. How many secondary hydrogens? Aiden says 2. How many tertiary? So 1. So the sum of that is 12, right? That's the total count. 3, 6, 9, 10, 11, 12. So we'll note as well that of the 3, 6, 9 methyls, there's 2 types there, right? So I just want to say that equals 6 plus 3 because these methyls are the same, but they're different from that methyl. So this is sort of what we're doing in this type of problem. We're given a molecule, we classify. Now what we want to do is for each change in enthalpy for primary, secondary, tertiary, for chlorine and bromine, we want to explain the reactivity values with a plot. And so, as I said, you know, the material from chapter 6 really blends into 10 and 7 in terms of contextualizing it. So this plot here is called a reaction coordinate diagram. And it looks like my copy paste cut something off here. We'll call this time. So time on the x-axis, we're going to say reaction starts at 0 and then it proceeds. So I'm not showing you the whole reaction. And usually the reactions are on nano or picosecond scale, so it's super fast. The y-axis is the energy, and that's what we've been dealing with in kilojoules per mole. So let me point out a couple things here. So here we're starting, this is our starting material right here. This is the 2-methylbutane. Now for chlorine, we said that the formation of the radical is exothermic. So on the reaction coordinate, going from the starting material, moving forward, time is moving forward, things are changing. As the radical forms, we're evolving energy. And so we typically depict that as going from some arbitrary energy to evolving energy. That's heat. It's negative, right? So that's what we mean here is we're going up to this thing called TS, and then we're going down to the different radicals. So here they are: primary, secondary, tertiary. We said the values for those were -21, -34, and -50. So how do you want to conceptualize or think about what a reaction coordinate diagram is? And again, what these things are the different radicals. So let me just draw them out so you see them. So primary radical, what's the structure of that? Say we're putting the radical there. Or it could be the other methyl group. The secondary radical, and then the tertiary radical. So that's the actual structures. So if you were a very, very tiny person and you're a couple angstroms tall and you could see this, and you could actually see this, even though this thing is flat, these reaction coordinate diagrams are actually three-dimensional surfaces. So if you've taken calculus 3 or 4, you talk about these 3D surfaces and how you can move around on them. So this is a slice of that surface. You're starting here, you're this tiny little atomic sized person. You're walking up this hill. Notice that as you walk up this hill, you're a little bit higher in energy because you're reaching this thing called TS, which is transition state. A transition state is very fleeting. And by fleeting, I mean in terms of if we go down to the time axis, it really only exists for femtoseconds. So that's pretty quick. What does that mean? As you walk up to this top, this time is so short, you either fall back this way or you immediately fall forward to one of the radical intermediates. So the key things you want to take away from this: a transition state is the top of a curve. An intermediate is a well. It's not the final resting place because this is not our final product. So let me just put that word there, intermediate. Now the time, so because this is a well, the intermediate can exist longer, and we can say we'll say picoseconds, if I can spell right. So understand conceptually, when you're at the top here, the existence time is much shorter. But when you're in a well, it's longer. And if you really like math, you can study these things. There's computational chemistry, software packages. I sort of use one in showing you guys three-dimensional structures for molecule to lecture and whatnot. But this is a vigorous area of research as well, is understanding the electronic structure of these intermediates and how long they can exist. So are we good with what this is sort of telling us here? So I'll sort of, for demonstration purposes, show you that from where you start to where you end up in the intermediate, if you go down, that's exothermic. So now let's go to our bromine plot. again, we said those values were positive now. And so again, we're moving from 0 energy up. So we write those values in. We have plus 13, plus 29, and plus 42. Our transition state. Notice the energy of the transition states are all at different energies. Now, what I really want you to focus your eye on is for chlorine, notice how they're all sort of the same, right? You're moving up to the same sort of transition state, and then they all disperse down to different energies. Here, the energy levels are higher. And so that's why we say for tertiary, when you're walking up that hill, for tertiary, you have less energy to walk up. Then secondary, then primary. So the gist of this is when you have a molecule like this and you're using bromine, tertiary is more favored than secondary than primary. When you use chlorine, you're going to get a mix because all of these values are negative. So let's put this in. You're going up, that's positive, so this is endothermic. Are we satisfied with that explanation? So I'd like to spend maybe 5 minutes on the next slide. Or excuse me, the next couple questions here. So these are questions to you. Then I have like a prompt. That's a pretty complex problem that you can work on your own, but I think it's a very good review of all the concepts we've learned from the start of this semester till now. So here's some questions for us that we can consider. I think there's 5 questions here. Which species represents an intermediate form during the reaction shown? We're taking propane, 1, 2, 3 carbons, hydrocarbon propane, molecular chlorine, light. Now you read this, you're substituting a secondary hydrogen for chlorine and forming HCl. What is the intermediate in this process? Again, due to COVID, you know, in how I structured the class this semester, you're taking unit module exams, and there is no final exam. So let me repeat, if you have not read the syllabus yet, there is no final exam in this course. You will be done with this course before the Thanksgiving break. After Thanksgiving, you do not have to take a final. So in some sense, you have it a little bit more straightforward than a normal face-to-face, because if you saw this reaction question on a final exam, it's not necessarily in a context of the module. So you have to recognize, okay, what is happening, and then verbalize that to yourself. What's changing from this to this? Okay, I see one of these hydrogens is going away and it's substituted for a chlorine. Then you have to look at the conditions and say, okay, is this a radical, a carbocation, a carbanion, or am I starting with an alkene doing an addition? So the correct answer is A, because it's in the context of what you've been learning. It's a radical substitution. So which is a propagation step in free radical chlorination of ethane? So in a radical mechanism, there are three main types of steps: initiation, propagation, and termination. This is asking you for propagation. So what do we think is the best response for a propagation step? Just think about what the word propagate means. So it sort of has to pay it forward. In a radical propagation step, the product of that step has to be a radical. So that leaves choices A or D. But A is not a viable choice because what word would you use to describe what's happening in A? So Ian says nothing. I'm going to challenge that word response. Max says it has the same molecule on both sides, which is true. So my challenge to Ian is something is happening, but it's like identity, right? So if you've taken like matrix algebra or something like that, you learn about these identity functions. So how could you prove that that is actually happening, where one ethyl radical is abstracting a hydrogen from another, but it's actually identity? So there's ways you can prove that that's happening. But yeah, it's not a propagating step because you're not generating a productive radical to go into the cycle. If you notice in step B, or choice B, you have ethyl radical, ethyl radical. When two radicals combine to form a neutral product, that's called a termination step. We also see that in C, ethyl radical plus chlorine radical combining to give chloroethane. That's a termination step. So D is the correct choice. Ethyl radical abstracting chlorine, generating product in chlorine radical. So why are radical reactions really complex? Because just because we want this to happen on paper doesn't mean nature has to obey what we want. So all of these other things are viable processes, and that's why it's sort of tough to control these from, if you were working for like Shell or British Petroleum or something and you were doing this sort of chemistry, you have to know the thermodynamics and kinetics for each initiation, propagation, and termination step so that you're only getting like the desired product and you're minimizing the formation of these other byproducts. So which radical is the most stable? So we're seeing some D as in dog. Yeah, again, you're looking to classify the radical. So we see a couple more responses here. Yes, D is tertiary and it's resonance stabilized. So why did you choose D and not C? C is tertiary. What's the difference between C and D? Or excuse me, C is secondary. I'm thinking of B. So if you just classify them, you can get to this. Now, the difference between B and D is that D is resonance stabilized. B is not. So there's sort of a conundrum with C, though, because C is resonance stabilized, but if you look at that, they're both secondary. So D has tertiary, secondary, so D is the winner. Does anyone know who this dude is and why I would put this awesome picture on here? I'm assuming everyone was born, say mid 90s, and they have no idea what this is, what movie this is from. Who is Jesse McCartney? So this is Christian Slater. The movie is called Gleaming the Cube. You should watch it. It's a good family flick. He has a brother who gets like kidnapped, I think, and he rides around on this bitchin' skateboard to get his revenge against the kidnappers. Total angsty movie. I think you might dig it. So let's check out this one. What is the expected product from this reaction? So now pay attention to the molecule, the conditions, and what you think the correct product might be. So when we say expected product, we're talking about the major product. So here's another movie for you. That's Kevin Bacon. He's got a raspberry beret on here. He's a bike messenger, I think, in New York City. This is another cool movie. You could say it's a radical movie. So D is the correct answer because why? When we look here, we have primary, secondary, tertiary, secondary. The molecule is symmetric. So when we compare those sets, we said bromine really only goes after tertiary, and that's a tertiary substitution, so D is the correct answer. So here's this dude. He's radical. This problem is asking you to identify the weakest CH bond. So you have HA, HB, HC, HD. A radical is going to go after which type of CH bond? I don't think this guy was a serial killer. So when you compare these, there is a Rubicon, a line in the sand amongst the different types. That's definitely not Charlie Manson. Can you tell me what is the line that separates these different types? I'm thinking of a concept. So hybridization. So if you look at the carbon hybridization, HA, this carbon, that's sp2, B, C, and D are all sp. So what implications does this have? That means we're really only considering these in terms of which one's going to be abstracted easiest, or stated another way, which one has the weakest CH bond. So between B, C, and D, which one do you think wins? So how can we differentiate this? We say HD is primary, this is secondary, this is secondary. So we've eliminated that, we can eliminate D. Now we're stuck between two secondaries. Of the two secondaries, HB and HC, which one wins and why? Ian says because it's nowhere near the primary. Yes, that is a true statement, but it's not the correct reason. So Aiden says it's resonance stabilized, so that's true. So when a radical abstracts HB, you generate a secondary radical that's stabilized into the benzene ring through resonance. So HB is the weakest bond. Okay, so we have one more. What is the expected stereochemistry of the organic reaction, organic product from this reaction? So we have this compound here, which although it's not drawn, it's stating that this compound is the R isomer. When it's treated with molecular chlorine and heat under radical conditions, you generate substitution of this hydrogen for chlorine. Then it's saying of this product, you get the S isomer only, the R isomer, equal amounts of R and S, or unequal amounts of R and S, and Y. Okay, do you guys know who these people are? So they're on the slide because they're radical too. Yeah, they're Saved by the Bell. So the answer is C, because when the chlorine radical abstracts this, you're changing from sp3 to sp2 hybridized carbon, where the radical is residing in the p orbital, which is achiral. When you complete the rest of that mechanism, the chlorine can add from the top face or the bottom face to get you equal amounts of R and S. So an equal amount of two enantiomers is called what? Remember what that's called? So racemic mixture. And if you were to take some of that, dissolve it in solvent, and measure it on a polarimeter, what would the specific rotation be? So because it's racemic, it's 0. And again, why is that? When you have an equal mixture of R and S, the R will rotate the light one way, the S will rotate it back the opposite way to get 0. So here is a prompt for you to consider. So I'll leave this up for about 3 minutes, and then we'll finish off the rest of this session with a slide that's going to transition us into Chapter 7. So the prompt is, consider the possible linear and branched constitutional isomers of a hydrocarbons with 6 carbon atoms. So you're only dealing with CH. How many possible linear and branched constitutional isomers have 6 carbon atoms? So that's your first thing in this prompt. Of those, how many monochlorinated isomers are possible for each? Keep in mind, they're going to have the same molecular formula, same mass. So knowing that, how do you differentiate all of them? So to help you logically figure this out, write the structure for each and the IUPAC name of each. If you're ambitious, look up the melting and boiling points. How many unique carbons does each have? How does the halogen shift the carbon peak? How many unique sets of hydrogen? What is the hydrogen ratio in each? How does the halogen shift the nearby hydrogen peaks? What is the probability of each unique hydrogen being substituted? Rank the product distributions by CH classification. How would that change if bromine were used? So let me just give you a hint based on my analysis. And I know this is going on video, so I'm going to do it really fast so you can't pause and read it, but there's mine. So I got 23 possible products. So see if you can, again, draw as many as you can. It's good practice for naming things, thinking about proton, thinking about carbon, putting all of these things you've learned together. In my estimation of teaching and learning, that's the best way, is if it's in some sort of context. So give that a shot. See what you come up with. But I'd like to move on to the following prompts in our last couple minutes here. So maybe we'll use the blue lightsaber. Consider the following. So these are a bunch of facts and observations. And again, what we are doing is we're putting all of the stuff we've learned so far together. So we've learned stuff about chapter 10, radicals. Now we're transitioning into chapter 7, which is substitution reactions. Consider this. Methane is a nonpolar molecule. Methane reacts with chlorine to give chloromethane. Chloromethane is a polar molecule. Methane does not react with sodium chloride to give chloromethane. Methane does not react with sodium hydroxide to give methanol. Chloromethane reacts with sodium hydroxide to give methanol. Methanol is a polar molecule. Explain the above observations using your chemical knowledge you've gained so far in this semester. So let me write out the equations that are happening here. So methane reacts with chlorine to give chloromethane. So methane is nonpolar, chloromethane is polar. Methane does not react with sodium chloride. So I'm going to put a big red X through that. Methane does not react with sodium chloride to produce chloromethane. Methane does not react with sodium hydroxide to produce methanol. Chloromethane reacts with sodium hydroxide to give methanol. So I'm going to draw that here. Methanol is a polar molecule. So how do we explain these observations? So methane reacts with chlorine to give chloromethane. Chloromethane can react with sodium hydroxide to give methanol. However, methane will not react with sodium chloride to give this, chloromethane. Methane will also not react with sodium hydroxide to give methanol. So we started this semester by learning about alkanes. We spent chapter 10 learning about the substitution of H for chlorine. Chapter 7, we're learning about the substitution of a halogen, say chlorine, for some other group, hydroxide anion, to give this. So we're going from a haloalkane to an alcohol. That's a functional group transformation. Look, substitution of H for chlorine, substitution of chlorine for OH. This happens through a radical mechanism. This happens through a polar mechanism. So for now, I'm just going to say a polar mechanism is 2 electrons. So remember here, radical was 1 electron. Now, look at here, the common thing in all these reactions here, H, H, H. We want to understand why these reactions do not occur. We already understand why this occurs and the mechanism which happens. When we substitute the H for chlorine, we can actually get this reaction to go forward. But we cannot substitute H for Cl using this reagent, or H for OH using that reagent. So chapter 7, we're going to learn why that is. And it's because we introduced this group into the molecule. And it's going to relate back into this table here, which is the relative strength of acids and their conjugate bases. Now, we're going to specifically talk about conjugate bases in the sense of the term called leaving group. And so we saw with very strong acids, they have very weak bases. Now that's coming back into play. So on Monday, we'll pick up with this and we'll understand the polar type of substitutions presented in Chapter 7. If you have questions, again, shoot me an email. I answered someone's email through a video response. I thought that worked pretty well, so I might just do that from now on to send you a short video of your questions. So other than that, start working on your homeworks in Wiley. And then there's 2 professional development activities. One is an independent or individual development plan, and the other is a personal statement. So start working on those as well. But otherwise, we'll see you Monday, all right?